All right, thank you very much for having me here. Today we are going to look at a new chapter, chapter 5, which is on 5.1. It's known as waves. So today we're looking at different types of wave and trying to have a better understanding of what waves are. So I need you to look at page number 180. So I want to look at page number 180 on wave motion. So it says here, wave motion is a transfer of energy without the transfer of matter. What does it mean? It means that energy can move, but there is no distortion to the matter itself, or there's no disturbance to the matter itself. If you look at, let's just say, the sound wave, at this stage while I'm talking, you're able to hear me. And that is the reason why you can hear me is because of the transfer of energy. And also, if you look at ocean wave, for example, and after this pandemic, let's say you go to the ocean, if you come across ocean wave, the reason why ocean can move around on that particular water surface, even though there's no disturbance really to the water itself, but because of the transfer of energy, it allows what we call the wave motion. So today we're looking at two different types of wave. We have the transverse wave, we have the longitudinal waves. So transverse wave and longitudinal waves. So let's look at the next slide. So as you can see here, once again, we have two different types of waves. We have the transverse wave and longitudinal waves. If you look at transverse waves, it says that transverse waves makes the particles vibrate up and down. If you come across a particular wave, it goes up and down, up and down. Think about the ocean, for example. If you go to the ocean today, you will see that the wave is going up and down and so on. That is the transverse wave. So make sure you're very clear. Transverse waves means that the particles are vibrating up and down, which means here something called the crest and trough, something that we are going to discuss today in the next few slides. So the crest is the top of the wave and the trough is the bottom of the wave. So you say example of transverse waves are waves that you see on the ocean and the waves that you can flick along the rope, slinky, spring, or hose. So you see that in the longitudinal wave, the particles vibrate backwards and forwards in the same direction. So if you come across a wave on say that is going up and down, that is a transverse wave. But if you're talking about wave or particles, they are moving front and back, that is an example of a longitudinal waves. So if you're talking about longitudinal waves, say particles vibrate backward and forward in the same direction as the wave motion. So it's an example of a longitudinal wave because the particles vibrate in the same direction that the wave propagates in. Alright, so something for you to think about. If you talk about ocean wave, for example, it's an example of a transverse wave because the wave is going up and down, or the particles is vibrating up and down. If you come across the vibration of particles that is front and back, there is an example of longitudinal wave. An example of longitudinal wave will be sound wave in that particular sense. Moving on to the next slide. So if you look at this diagram here, and this diagram is in your textbook, so you can check it out. If we look at this diagram here, we can see that there is a difference between the transverse wave and the longitudinal wave. So the one that I've highlighted orange, here is the transverse wave. Can you see? Let's just say if this is a particular spring, and then you are moving the spring up and down, that is an example of a transverse wave. Always try and picture something like the ocean waves, for example. If you really look at the ocean, and then let's just say that this wave that is coming or moving towards you, you know the wave is going up and down, up and down. So something for you to consider is that when the transverse wave passes through a material, the individual particles of the material move at right angle to the motion of the waves. And it is of right angle. You see that the wave is going up and down. It's not moving towards your direction. It's not moving backward, but it's moving at what we call perpendicular to you, or in this case, the right angle to the motion of the wave. So going back to the words that have been mentioned before, if you look at this particular diagram here, so the one at the top here will be known as the crest, and then the one at the bottom will be known as the trough. So I'll just put C stands for crest, and then we have T that stands for trough. All right, so something for you to consider. All right, if we look at longitudinal waves, and going back to this slide here, and let's just say I highlight this in light green. So longitudinal wave, the wave is going forward and backward. So it says when the longitudinal wave passes through a material, the particles of materials move backwards and forward in the line with the direction of the motion of the wave. So once again, if we are talking about, let's just say, ocean wave, you are referring to as an example of a transverse wave. So moving up, down, up, down. If it's moving front and back, and we get what we call compression and rarefaction, as you can see in this particular diagram, compression and rarefaction as highlighted here. And this is part of what we call the longitudinal wave. The waves is moving forward and backward. All right, think about the difference between, in this case, between the transverse wave and the longitudinal wave. Moving on to the next slide. All right, so wave properties. It says the number of waves produced each second is called the frequency of the wave. Frequency is measured in hertz, Hz, which means cycles or number of waves per second. So think about this, make sure you know what the number of waves means. So it says that number of waves produced each second is called the frequency of the waves. Frequency is measured in hertz, which means the number of waves per second. Number of waves per second. So let's just say that if you have 5 hertz, which means that you have 5 waves per second. So it says here wavelength is the distance between two successive waves and is usually measured in meter. It says the wavelength of some radio waves is several kilometers, whereas the wavelength of visible light is less than 1,000 of a millimeter, which is very small. So it says that the amplitude of the waves is the maximum distance it extends beyond the meter position. All right, there's some new words for you. There's two main things, or there's 2 to 3 main things you need to know from this particular site. We need to know something, what is known as the frequency, what is known as the wavelength, and what is known as the amplitude. So there is a correlation between frequency and wavelength itself. That's something we are going to discuss in the next few slides. And we're talking about amplitude, we're talking about strength, in this case the distance that it can extend from the meter position. So if the particular strength of that particular wave is very strong, it will have a larger amplitude as a result. So I'll show you in the next few slides on what this means. So if we look at this diagram here, you can see that there is a difference between the transverse and longitudinal wave. Once again, transverse wave is when the wave is moving up and down. You can see a few different terms here that you need to know what they mean. You have something called the amplitude. So amplitude is the extension of that particular strength of the wave from the meter position, as we previously mentioned. So it says here the amplitude of the transverse wave is the height of the crest above their normal meter position. So we talked about crest and trough previously. So if it's going downward as well, if from the meter position to the trough, is also known as the amplitude. When we are talking about wavelength, we are talking about one particular wave, the distance of one wave. So if you look at wavelength here, say wavelength of the transverse wave is the distance between one crest and the next. You can measure it from one crest to another, you can measure from one trough to another, or you can measure from one meter position to the subsequent. When I say subsequent, it is the meter position of the second wave. So it must be a complete wave itself. So make sure you know the difference between amplitude and wavelength. And when we are talking about wavelength, later on we will be using the term frequency to describe a wavelength to a certain extent. And amplitude here, once again, is the height of the crest, or you can also say is the height of the trough from the meter position. So that is referring to the transverse wave. When we are talking about longitudinal wave, you can see there's something called the rarefaction and compression within that particular wave. So it says the wavelength of longitudinal wave is the distance between the compression and the next closest compression, or rarefaction and the next closest rarefaction. So if you look at this diagram here, the one that I'm going to highlight right now in orange, this is what we call the compression region. Can you see there's many of that particles that are next to one another? And this is what you normally find with sound waves. So this is the compression wave, as compared to, let's say, if I highlight the next one in blue, and this region will be the rarefaction region. All right, which is why sometimes if you're in a room, if you put like a 2 speaker or speaker in front of you, you may not be able to hear the sound as clearly as some other parts of the room. It has a lot to do where you are standing. If you're standing in that particular region that is of the compression region, you will probably hear more clearly as compared to the region that is of rarefaction, that's less of that particular particles. But the point here, make sure you know how do we use wavelength amplitude and to a certain extent frequency to actually describe our transverse and longitudinal wave, and we know the transverse wave is when the wave is moving up and down, up and down. If a longitudinal wave is when the wave is moving forward and backward, and so on. Moving on to the next slide. So wave properties. It says that for two waves of the same frequency and wavelength, the larger the amplitude of the wave, the more energy is carried by the wave. Do we agree? If you look at ocean wave, for example, if you go to ocean today, I mean, after the pandemic, you will see that if that particular wave is very strong, it will have a larger amplitude. It will have a very tall height, or the height will increase as a result. Eventually, if there will be more strength when it's coming towards you, and probably even pull you into the ocean if it's like a tsunami and so on. So in this case, we know that we have, this is the low amplitude wave. It has very small amplitude. And once again, how do we measure amplitude? It's from the middle point, either to the crest or to the trough. And for high amplitude wave, you can see that the amplitude has increased dramatically as compared to a low amplitude wave. So once again, how we measure the amplitude is from the middle point to the crest, from the middle point to the crest. So I'm drawing an arrow here to show you this is how we measure the amplitude of the low amplitude wave, and you can do the same for the high amplitude waves as well. So from the middle to the crest, or from the middle to the trough. Moving on to the next slide. Alright, so we're going to continue on wave properties here. Page number 181. As you can see in this diagram, and based on what is mentioned here, it says the frequency is the number of waves passing every second. It says the more bunched up the waves, the higher the frequency and the shorter the wavelength. So before this, we were talking about amplitude. If you see the strength of that particular wave is greater, let's just say that the distance between the crest and from the middle point has increased, which means that the amplitude of the wave has increased. So in this case, we are referring to as a frequency. We are looking at what frequency is, and frequency is the number of waves passing every second. It's measured in hertz, as mentioned before. If you have 3 waves per second, then the frequency will be 3 hertz. If it's 5 waves per second, it will be 5 hertz. So you have wave A and you have wave B. So it says that given that wave A and B are traveling at the same speed, wave A has a higher frequency and shorter wavelength than wave B. If you look at wave B, it says that wave B has a lower frequency and longer wavelength than wave A. Do we all agree? Probably we do. As you can see, wave A has a larger frequency because the wavelength is a lot smaller. So once again, frequency is the number of waves passing every second. So it has a lot to do with the wavelength. So the higher the frequency, the shorter the wavelength as a result. So in this case, you can see that wave A will have a higher frequency and shorter wavelength compared to wave B, because within the same amount of time, you can see that it has produced a lot more wave as compared to wave B. So wave A itself, if you look at number of waves, will be 1, 2, 3, 3.5 wave, because the last one is not really completed. And wave B only has 1 wave. So 3.5 to compare to 1, you can see that wave A will have a higher frequency. At the same time, it have a shorter wavelength, which means that wave B will have a lower frequency, have a longer wavelength as compared to wave A. Moving on to the next slide. Alright, so we are looking at the wave equations. The wave equation is the relationship between the speed, wavelength, and frequency of the wave. So if you look at this particular diagram here, you can see our skill builder. It says that wave equations, the speed, wavelength, and frequency of a wave depends upon each other and are linked by a formula called the wave equation. So make sure you know what the wave equation is. So you have, if I go to the bottom here, you have F. F is the frequency of the wave, which is in hertz. We have B. B is the speed of the wave, which is in meter per second. And we have the wavelength, or lambda. If you see that particular lambda sign, that sign is known as the lambda sign. It's the wavelength of wave. So it says that lambda, as mentioned before. So your frequency equals to the speed of wave divided by the wavelength of the wave. So a few things that you can get out of this. We know that when the wavelength increases, the frequency will decrease. If the speed of wave increases, the frequency will also increase. So think about that. So if I move on to the next slide, and I'll move on to the slide right now. Alright, so this is probably the final slide that we have. So we have the formula as what we have discussed previously. Sorry about that. And then here we have the word example. So it says here, at the beach, a wave hits the shore every 10 seconds. If there is 6 meters between successive waves, calculate the speed of the waves. So if you have a wave that hits the shore every 10 seconds, we know the frequency will be 1 divided by 10. Why? Because frequency is looking at number of waves per second. So in this case, the number of waves is 1 per second. So we know that the frequency will be 0.1 hertz. If we look at the wavelength, we know the wavelength is 6 meters because it's 6 meters between successive waves. So wavelength is 6 meters. If you use the formula, we know the speed. The speed here will be frequency multiplied by the wavelength, which is 0.1 multiplied by 6. We get 0.6 meters per second. So what we will do right now is that we're going to try one question, and then I'll get you to complete the remaining question when we return to school, and we will discuss, or we return to our classroom discussion, and we discuss more on the other questions as well. So let's look at question number 1. So try yourself. Question number 1. It says a child playing a slinky shakes it backward and forward 5 times per second. 5 times per second. So you can sort of picture this is moving forward and backward. So it is an example of a longitudinal wave. It's not transverse wave, because with transverse wave, the wave is moving upward and downward. So in this case, forward and backward is an example of a longitudinal wave. We say it's a wave of the slinky are 30 centimeters long. Calculate the speed of the waves. So a few things that we can write down right now. So let's do question number 1. So question number 1. So few things that we can get out of this. So we know that in this case, the frequency is the number of wave per second. Number of wave per second. So for question number 1, the number of wave per second will be 5. So we can say that the frequency will be 5 divided by 1. Why is it 5 divided by 1? Because we have 5 waves per second. So 5 divided by 1, we will have 5 hertz. So 5 hertz. Alright, so frequency is done. If we look at the wavelength here is of 30 centimeters long. So what you need to do this is that you know the formula is a meter for the wavelength and for the speed as well. So what you need to do is that you have to convert the wavelength, which is from 30 centimeters to meter. So we know the wavelength here. So this represents the lambda, which is the wavelength. You know the wavelength is 30 centimeters. So what you need to do, you need to divide it by 100. So 30 centimeters, eventually what you will get is that you have 30 divided by 100. So 30 divided by 100, you're going to get 0.3. So 0.3 meters. So you can write that down right now. 0.3 meter. So that is the wavelength that you have. So now it's asking for the speed of the wave. So using the formula, they have given you the frequency, they have given you the wavelength, and they are asking you for v. They are asking for v, which is the speed. So how do we find the speed? So if you use the formula, we know the formula is v equals to f multiplied by the wavelength. So v equals to frequency, which is 5, multiply by the wavelength, which is 0.3. You know that your speed will be, in this case will be 5 times 0.3. 5 times 0.3. So your answer will be 1.5. So in this case, the speed will be 1.5 meter per second. 1.5 meter per second. And that is your final answer. So make sure you know that the speed in this case is 1.5 meters per second. How do we find? You have to use the formula, which is v equals to f multiplied by lambda, which is the wavelength. We know the frequency is 5 hertz. the wavelength is 0.3 meter, so the speed needs to be f multiplied by lambda, which is 5 times 0.3, so we get 1.5 meter per second. Alright, so I need to try out on question number 2 and 3, so we discuss that more back in our classroom discussion, and then I will see you then. Make sure you do complete the school box questions. So school box question for this week, make sure you do complete the work and you upload it onto Dilbert on school box itself. If you're welcome to ask me questions on social stream and or email me your questions as well. So I'll see you then.